diagonalizability. Let's just look at it again. One fact which I quickly skimmed through is, you see, what I'm doing over here is essentially matrix multiplication. Suppose if you have two matrices where B looks like this. This is the first column of B, second column of B, and say nth column of B. Okay, so I'm saying, say, this is a P by M matrix and this is a M by N matrix. Okay? This product by our matrix rule is nothing else but this matrix A times the column 1 of B, A times the column 2 of B, and A times the column N of B. Observe, each column is a member of Rm. So A times this is a member of Rp, right? P. So there are P rows now and N columns. Okay? Okay? So now, you know that a matrix, we say that A is diagonalizable. So this is the definition. If there exists a non-singular matrix C such that is a diagonal matrix. Obviously, I'm speaking about square matrices now. Okay? Now observe. Tell me this. I could write also in this way instead of this. Let me write it in a better way. CAC inverse. Okay? So if you tell me that CA is C times a diagonal matrix, usually we write the diagonal matrix in this way. Okay? So, observe. So this tells me C times the first column of A, C times the second column of A, C times the nth column of A. This is equal to, now, pick. This is C times, okay, C times lambda 1 0 0 0 0, right? So this is actually, no, C times, right? where these are the standard bases, right? 1 0 0 0 0 1 0 0 and so on, right? Now let's have a look. What is, let's see, what is this matrix? Any matrix times E1. N cross, so it is going to be a vector, right? What will it be? The first row, only the first one element will come in, right? Second row, only the first element. So this is actually nothing else but the first column of C. So in general, if you take an I, this is the ith column of C, right? So you see, we get over here that C times so we get lambda 1 times the first column of C, lambda 2 times the first column of C. What mistake did I do? There's a mistake somewhere. There's a mistake, I believe, somewhere. Cx is equal to there's a mistake. Where is it? C times 2. I want to say something. Okay, let's stop. I made mistake somewhere. Okay, but since I messed up this step, this would have been a much better way out, but I made some mistake somewhere. I cannot get it now, and some mistake, please forgive me. The thing that I wanted to say is diagonalization is actually same as having a basis of eigenvectors. Okay. Now we are going to utilize this, but we also saw last time for matrices in general. Okay. You may not even have an eigenvalue. Okay. So, for instance, I give the example 0 minus 1 1 0. Yeah, that doesn't have any eigenvalue. Okay. But I'm going to show the first thing today is that that will be our first theorem today. Every eigenvalue of a real symmetric matrix
Remember, the eigenvalues are nothing else but the roots of the characteristic polynomial. This characteristic polynomial has coefficients reals. Okay? So by the fundamental theorem, there always exists a complex root. But with coefficients real, we only know that the roots appear in conjugate pairs, and unless it is odd, we are not guaranteed of having any real root at all. Okay? So, the next question that therefore comes up is how, in general, matrices may not have real roots, but every real symmetric matrix has eigenvalues real. Okay? Now, how do we prove this? So the proof comes in this way. Let be real symmetric. So that means I know that A transpose is same as A. Right? Now, consider this polynomial. But I allow I'm considering this polynomial as a polynomial with complex coefficients.
Excuse me, friend.
Yes?
Yes, you are talking about symmetry. Can you just enlighten us a bit so that we are together?
Symmetric means A transpose is equal to A. Hello? Yes, could you get me? This one is just
really.
Why?
Yeah,
I couldn't get your question. I couldn't get your question.
Yeah, I just wanted you are talking about symmetric matrix, and then at least and I just thought maybe you can just enlighten us a bit with just a small example.
So if you interchange so the identity matrix is symmetric. What is A transpose? You just interchange the rows and columns. So if you for instance, if you take a matrix like this, its transpose is nothing else. The first column becomes the first row, and the second column becomes the second row. That's it. So symmetric means that if you interchange the rows and columns, it doesn't.
Okay, thank you, sir. Thank you. President.
Now, consider this polynomial which I have defined like this, but I have allowed my variable z to take complex values. Okay? Right. Now, this is a polynomial, obviously. The coefficients okay, why do I need this? Now, by the fundamental theorem, I know that this has a complex root. Okay? by the fundamental theorem, there is a complex number such that okay. Now what does P lambda equal to 0 mean? This means that determinant of this is 0, right? So this means that is non-singular, sorry, is singular, and because it is not invertible, so it's singular. Right? Okay? So this means that if I consider this equation, but now this Z is in Rn, in Cn. This has a non-trivial solution. Okay? So, this means that it is equivalent to say that there exists So I have Z, an n-tuple of complex numbers, not all 0, such that Az is equal to lambda Z. Okay? Alright. Clear? So, you have Az remember, Az is also a member of Cn, so each entry is actually a complex number, right? So I can take the conjugate of each entry. So let me tell you, if I have Z in Cn, by Z bar, I will mean that n-tuple where I have actually taken the conjugates of each of the entries of Z. Okay? So this is a symbol. Okay? I define this symbol. So this is some kind of a definition that I am making. Okay? So, now so this is a member of Cn, so I can take, using this definition, right? Okay? Now, let's look into Az. How do I get the first entry of Az? Is the first row of A and taken with Z, right? So Z1 times A11 plus Z2 times A12 and so on, right? So what would be the complement of it? It will be Z1 times A11, Z1 bar, conjugate of Z1 times conjugate of A11, right? Okay, wait. I'm just looking into the first, suppose A is.
So does this mean that there is a column?
Yes, there is in field, right? So it's
treated as a column.
yes. So suppose if A is looking like this, then AZ, what is this? This is A11 times Z1 and so on. Conjugate of this, by definition, at each point you are going to take the conjugate.
Oh.
Right? But you know, conjugate of AB is conjugate of A times conjugate of B, and conjugate of A plus B is conjugate of A plus conjugate of B. So conjugation actually preserves the addition and multiplication. Right? So therefore, AZ, this will be this actually, right? Okay?
So it applies to...
Right, that's the definition.
So doesn't it apply individually to each?
Yes, this is the first member. This is the second member.
Okay, but you drew the line across.
Across, yes. So this is the first member. So across.
Oh.
Yeah, I'm simplifying.
Oh, okay.
Okay, so this one will be I did two steps together. A11 bar, but A11 is a real number. So A11 bar is same as this, right? So you get similarly this. So this left side actually comes out to be A times Z bar. Right? See? Okay? And this one again will be lambda bar times Z bar.
So lambda is basically a real number too.
No, lambda was a complex number, remember?
Oh, okay.
Lambda, I'll prove that lambda is a complex number, but so far we have only lambda to be a complex number. Right? So we have this also. So we know that AZ is equal to lambda Z implies AZ bar is equal to lambda bar Z bar. Okay? So therefore, now I am looking into this Z bar. Remember, this is a column vector, right? N cross 1. Z bar is considered as the matrix is an N cross 1. I transpose it. So it's 1 cross N times N cross N and times this. Okay? So this is a complex number. Right? This is a 1 cross 1 matrix. So it's a complex number. Right? So now I know that this is Z bar transpose lambda Z. But then lambda comes out. Right? Lambda is a scalar. So it will come out. Clear? Yeah.
So you included the conjugate of Z.
Z bar. Yes.
Transpose of the conjugate of Z.
Yes.
On both sides.
No, not both sides. This side is not the. So you see, this is why I did so. This is a 1 cross n matrix now. This is an n cross n matrix, and this is an n cross 1 matrix. So the product is 1 cross 1, which is a complex number. Right? And I'm saying, what is this complex number? It is this. Okay? Remember, since I should have written over here, since z is not equal to 0, this complex number cannot be 0. Okay? Why? What is z bar transpose of this is z1 bar z1, right? If that is not clear, so what is it? z1 bar z1 plus z2 bar z2 and so on, right? But z1 bar z1 is the modulus of z1 squared. That's a real number. Yeah? So it's the modulus of z1 squared plus the modulus of z2 squared and so on. Okay? And that's a real number. So since you told me that z is not equal to 0, at least one of them is non-zero. z1, z2, zn. So therefore one of their modulus is non-zero. Okay? So z1, modulus of z1 squared plus modulus of z2 squared up to modulus of zn squared, this sum cannot be 0. Okay? So that's what I was saying. Okay? Alright. So now, let's see. This, you told me that this is a complex number. So, this is same as its transpose. Right? Okay? Now let's see. If I transpose these matrices, I come to this. Yeah? So I come to.
So what happens to the alphabet T for the conjugate Z?
You remember, if you have matrices A and B which can be multiplied, AB transpose is B transpose A transpose. That's what I'm doing.
But what about the conjugate of Z?
So Z transpose, Z bar transpose is Z bar.
Oh yeah. Oh yeah. Sorry.
Okay? So this is what? Now this is Z transpose, but you told me A is symmetric. So this is same as A Z bar. Okay? But A Z bar is lambda bar Z bar. You told me. So this is same as okay? So okay? Sorry, lambda bar, Z bar is this, right? But this is same thing as this, right? So, lambda minus lambda bar times now this is a complex number, right? These are complex numbers, this is also a complex number. Okay? This is equal to 0, but I know that Z bar transpose Z is a non-zero number. So it forces lambda minus lambda bar is equal to 0, which says lambda is equal to lambda bar. Okay? Here I am using states. Yeah? So, what did I show? I showed that if I take a complex root of this equation, that complex number is a real number. Right? So, the fundamental theorem actually goes on to say it has all n roots, right? So, all the roots are complex numbers. And hence, by the same logic, all the roots are real numbers. Okay? So that proves this theorem. Okay? Alright. So, every real symmetric matrix has its roots, has its eigenvalues real. But the next step is actually the more fundamental step. See, having eigenvalues real is not much, because we saw last time that even if all the roots are reals, it could be that the eigenspace, that is the geometric multiplicity of some root, doesn't get equal to the algebraic multiplicity. Okay? And in such a strange case, we will never be able to diagonalize it. Okay? So the question is therefore that how do we ensure? So we have to ensure somehow that the algebraic multiplicity and the geometric multiplicity of the eigenvalues of a real symmetric matrix are same. Okay? So that's the next theorem. Multiplicity of an eigenvalue Now the proof actually depends on a very, very fundamental principle, another principle which is called the principle of mathematical induction. Okay? So I just outline what is it. The proof depends what is this principle? It's very, very simple looking principle. If
be a subset of natural numbers. Okay? Such that that if you have a subset of natural numbers which contains the first element, which is 1, and whenever it contains an element, it contains its successor, the next element, right? Then it must be the whole of natural numbers. Okay? So it is somehow telling you, how do I see? You can check. Why is this? Why is this induction principle very important? You can check a statement, a single statement. Okay? So, let's see. Let's take this case. You give me a real symmetric matrix of order 2. I can find its eigenvalues, I know they are real, and I can give you its eigenvectors. Okay? And, well, I can do it pretty in a general way. I can do it taking the matrix to be A, B, C, D. Okay? Good. But then I have only shown that every real symmetric matrix of order 2, the algebraic and geometric multiplicities are same. Okay? I can do the same thing for 3 by 3 matrices. I can do the same thing for 4 by 4 matrices. Okay? If I have enough time, I can do it for 10 billion by 10 billion size matrix also. But who tells me that it is true for every natural number? See, doing it for very large natural numbers doesn't actually tell you that it will hold. Who tells you that there is a natural number even after that for which it fails? Okay? So you collect. So what do? You make this set. You make this set of all natural numbers for which, if you take a matrix of size n by n, its real and its algebraic and geometric multiplicities are same. Okay? You take this set. So, principle of mathematical induction actually relieves you to how to give you this proof. The proof is, the idea is very simple. Show that for 1 is there. Okay? Assume that every matrix of order n, real symmetry, so n is in that set. Okay? And prove it for n plus 1. Okay? Then you have showed that 1 is in that set. If I assume that n is in that set, then n plus 1 is also in that set. So therefore, every natural number by induction. So induction principle is the only way, in fact, to prove a statement for all natural numbers. Okay? You can check for 1, 2, finitely many, but you cannot do it for, because of the simple fact that natural numbers is infinite. Okay?
So no matter how large you become and do your check, still there will be a person in the audience to say, who says that there is nothing beyond that where it will fail? Well, this is the way to show, no, it will never fail. Okay? So you get the idea now. So we take, how do we use this? As I said, let such that every square matrix of order n which is symmetric, the algebraic, I'm sorry, I should have said for every, the algebraic and geometric multiplicities of an eigenvalue So n shall be in that set if for every square matrix of order n, the algebraic and geometric multiplicities, for every square matrix which is symmetric, the algebraic and geometric multiplicities of any eigenvalue are same. Okay? Good. Surely, one. If you take any square matrix of order 1, it means something like this. What is an eigenvalue of it? Well, determinant of this minus lambda must be 0. That means lambda must be A. So A is the only eigenvalue. Okay? A is the only eigenvalue. Its dimension is 1, multiplicity is 1, so algebraic multiplicity is 1, so geometric multiplicity will automatically be 1. Okay? So there is nothing. So surely 1 is there. Okay? Assume that means you have assumed that whatever matrix, square matrix of order n may you take, if it is symmetric, then for any eigenvalue of that matrix, its geometric and algebraic multiplicities are same. That is what you have assumed by the saying this. Okay? Let A is a symmetric square matrix of order n plus 1. Let A be this, and so it has an eigenvalue. It is a symmetric square matrix, so I know all its eigenvalues are real. Okay? So take any one of them. Let extend to a basis taking, so x1 is non-zero because it's an eigenvector, okay, and you can extend anything, right? You can extend it to a basis. So let's take the coordinates. So what is the matrix? So if you remember, A is giving me a linear transformation, right? Okay? So let that linear transformation be taken as this. Multiplication by A. So what is the matrix? This. Remember, matrix of A. So matrix eigenvalue of F and eigenvalues of A are all same, right? That's how we define. So what's the matrix of F? Remember, this is the coordinates of B of F of x1. What is AX1? AX1 is lambda times x1. Right? So this matrix looks like what? It's lambda times x1. The first column is lambda. So the coordinates of this will be lambda 0, 0, 0, 0, right? Okay? So this looks like lambda and what would be the coordinates of this? Something, I don't know. Some matrix. Okay. Now there is another thing. I forgot, I should have said. This also shall be 0. Okay? This also shall be 0 because x2 is linearly independent of x1. Okay? So, since x2 is linearly independent of x1, over here there cannot be a combination of x1 coming in. Okay? So this also shall be a 0. Clear? So this becomes a matrix like this. Okay? Now I have a little bit of a problem. I know that A is symmetric. The symmetry of this tells me that C must be symmetric. Okay? So, and hence, but how many things? So this is a 1 by 1 matrix, right? So this must be n by n matrix, right? So C must be with C symmetric. Okay? What is A transpose? A transpose is just interchange the rows and columns, right? The first column, you see the first column is just lambda 0, 0, 0. The second column is lambda 0, 0, 0. The first row. So we interchange, it doesn't change. So this will be C transpose, right? A transpose is equal to A, so therefore C must be equal to C transpose, right? So C must be symmetric. But then I'm done. C is a symmetric matrix of order n, okay? And then every eigenvalue of this, every eigenvalue of C has its algebraic and geometric multiplicity same. Okay? One minute. Hence, x minus so herein I'm using the fact which I used last time also. Okay? Clear? Remember, I used this. If you have a matrix, squared matrix, here is one block, and here is something, say, and here is another block. Okay? The determinant of this is a square matrix. Okay? The determinant of this whole thing is actually the determinant of this times the determinant of this. Yeah? So that's a result about determinants of block matrices, which I referred to last time, and I said it is actually something which you should have got in the previous course. Okay, and I've given you material in the appendices, means in that, yeah? By which, if you go through that, you'll get this. Okay? Alright. So, now there can be two possibilities. Okay? Now let's see. What happens if this? It means that lambda is an eigenvalue of A, but not an eigenvalue of C. Right? And therefore, the algebraic multiplicity of, so, lambda is not this is the first thing that happens. So, the algebraic multiplicity of lambda is 1. Right? So therefore, the geometric multiplicity is 1. Okay? Here's what happens. So, lambda is an eigenvalue. But n I assumed to be a member of S. C is symmetric, matrix of order n, and lambda is an eigenvalue, so it's geometric and by an assumption. Okay? Since the algebraic whatever be the case, you started off with an eigenvalue of A, and you have shown that the algebraic and the geometric multiplicities of this eigenvalue is same. Okay? So that proves this. So what's the scenario? If I have a real symmetric matrix, then all its eigenvalues are real, and all its eigenvalues are real, and all its eigenvalues have same algebraic and geometric multiplicities. So, I know, therefore, as I said last time, I can have a basis